Hello everyone. In class 12, as we start with our syllabus, the first unit, the first chapter in the first unit, that is electric charge and fields, and in the second chapter, that is electric potential, we start our discussion with charge. So, basically, what is charge, and then how does the charge exist, and so on and so forth. We study the properties of charge, the different natures, and in the field around the charge. So how that field can be described, the field can be described using the electric field strength and also electric potential. uh, and then once we understood charge and its origin, so therefore it is important for us to store it, so that we can use it in some way. Okay, so today basically we are going to talk about a device that stores charge. It's called a capacitor. It's called a capacitor. So capacitor is basically a device that stores charge. Just like there are different things in which we can store water, so for our use. So basically, in the same way, so charge we can also store charges, and then the device in which we store that charge is called basically capacitor. Okay, now you in battery, what happens is that there is a chemical energy. Basically, if we talk about the chemical cell, and that chemical energy gets converted into electrical energy. So whenever we require charge from a battery, so the discharging of battery is very slow. So that means we get charge in a slow rate. And when compared to capacitor, so in capacitor no chemical reactions are going on, it just stores charge. And whenever we require a huge amount of charge immediately, so then we can use a capacitor, because capacitor, unlike battery, will discharge instantaneously. The whatever the charges is out there in the capacitor, it will give out everything at once. Okay, so that's the discharging of capacitor. So when we talk about capacitors, there are different forms of capacitors. Okay, so we started building capacitors in different shapes, different size, and then we are not going to discuss about all the types of capacitors right now. So our focus primarily will be based on a parallel plate capacitor. Okay, so if you ask me what is a parallel plate capacitor, then parallel plate capacitors are basically two conductors, parallel plate, kept separated by some distance. Okay, they are kept parallel to each other. So both the plate will have same area for us. Later on, if you go into higher level, then the area of the plate can vary, so it depends. But for our discussion, we will keep our area fixed, and the distance between the plates can vary. Okay, so we can bring the plates close to each other and or far to each other. But one thing you'll have to remember, that the distance between the plates should be smaller than the area of the plate. Okay, that is the one of the consideration that we will have to remember. So, and then how do we start storing charge in that capacitor? So that is the next question. So once we keep our plate parallel to each other, so once we keep our plate parallel to each other, so let me show you how it is done. We have a plate here and we have another plate here. It is kept parallel to each other. So the area of this plate is A, and we will also consider the area of another plate as A. I said we will only take this one example in which the area of both the plates are equal. And now let us consider this to be separation between these two plates, and this basically the distance of separation between two plates. Here we will consider it to be small d. Okay, so which can vary. We can bring the plate close to each other, or we can take the plates far to each other. Okay, so now then in one of the plates we are going to introduce positive charge, and the other one will be negatively charged. Okay, so how that is done? So since you know what I'm going to do, I am going to take some dq charge. Okay, I am going to take some dq charge one from one of my plate, and then put it into another. So in that way, one of the plate will be positively charged, in which from which I am taking a negatively charged electron, because you know in conductors there are free electrons. Okay, and that electrons I am going to put it into the another plate. So whichever plates gets the electron will become negatively charged, and whichever plates loses the electron will become positively charged. And now if you wonder, so how I am going to take charge, because since I am not able to pull the charge from one capacitor and put it into the another capacitor, so for that, what we are going to do, we are going to use external battery or external cell. Okay, So one of the plate, I am going to connect it to the positive terminal of a chemical cell, and another plate I am going to connect it to the negative terminal of an electric cell. So with that, what will happen is that since the positive will start pulling or attracting the negative charges from the plate, which is basically electrons. So the electrons will be pulled from the first plate. So as I show you here in the diagram, okay, and then the electron will be pushed to the another plate out here. So as I show you in the diagram, okay, now you can see here that one of the plates is losing electron. So the one which is losing electron will get positively charged here. Okay, it will get positively charged, and the other which one is gaining electron will become negatively charged. Okay, since the numbers of electron which is being pulled from the positive plate is being the same number of electrons is getting into the another plate. So if the first plate is going to get plus q charge, the second plate is going to get minus q charge. Okay, so this is how the charges are stored in a capacitor. Okay, and as you know, and if there are charges, a positive charge and a negative charge in this capacitor, the electric field will be developed from a positive plate towards the negative plate. And for this, I think we shall go back and then we shall recall the second application of Gauss law, that is the electric field produced by infinitely thin plane sheet. So was uniform, given by sigma by 2 epsilon naught. Okay, so which does not vary over distance, and we call that electric field as uniform electric field, which was created using this one, infinitely thin plane sheet. Okay, considering the symmetry, continuous charge distribution, and finally we derive that electric field strength will be equal to sigma by 2 epsilon naught, where sigma is the surface charge density in that thin plane sheet. So similarly, both the plates out here are thin sheets. So whatever the electric field will be produced by the first plate, the same electric field will be produced by the second plate. Okay, so so then if we continue to find what will be the total electric field between the plates, so then we will have to analyze at first what is the electric field of the first plate, and then continue doing it for the second plate as well. So then if I define E1 B electric field strength due to first plate, then E1 can be expressed as sigma by 2 epsilon naught. Okay, sigma, considering the surface charge density of the first plate is sigma, and since there's an equal number of charge in other plate, although opposite in polarity, therefore minus sigma will be the charge which will be there in the other plate. Okay, so let us give this as equation number one. Okay, so then similarly we will define E2 be electric field strength due to a second plate. So therefore, I can define E2 to be sigma by 2 epsilon naught again, because both are thin plane sheet. Okay. So, and we also know that electric field strength is a vector quantity. So therefore, if you want to see what will be the resultant electric field because of the plate 1 and plate 2, so you will have to first analyze this direction, in which direction they are directed in, and based on that we will use our vector law, whether has to be added, whether they has to be subtracted, or either we have to use some laws in order to get what will be the electric field strength. But in this case it is very simple, because as you know, the electric field from the positive plate will emerge in this direction. So we are calling this electric field as E1, and the electric field in the negative plate will terminate. Okay, so and then we are calling this as E2. So looking at this, analyzing this, or looking at the direction of E1 and E2, so we see that E1 and E2 are in same direction between the plates. So therefore, if you want to find net electric field strength between the plates. So I can write that electric field will be simply written as the sum of E1 and E2 considering their direction. And since we both know that E1 and E2 are having the value sigma by 2 epsilon naught, respectively. So if I add this, I am going to get sigma by epsilon naught. And how is sigma defined? Sigma is surface charge density. So surface charge density is basically a charge, total charge divided by the area, or charge per unit area. We as we describe surface charge density. So since sigma equals q by a, so I will be able to write this as q by a epsilon naught as electric field. So we will give this as equation number 3. So now let's discuss what will be the potential, electric potential between these two plates. And uh, that can be, we can derive that, or we can write that expression using the relationship between electric potential and electric field strength. You know that electric field strength is equals to the potential gradient, or a potential can be found by multiplying the electric field between what length or separation you are calculating the electric potential. Okay, so from the relationship between electric field strength and electric potential, we can write electric field can be written as V, and the separation between these two plates in this case is D. So I am going to write it as D. So because in that separation we are trying to determine the electric potential. Okay, so continuing on this part, so what I'm going to write now is I'll make V as a subject. So V will be E times D, and we know from equation number 3 E can be written as Q A epsilon naught, and there is D, so I will keep D as intact. Okay, and I will give this as equation number 4. Okay, so now we have got the expression for electric potential difference, basically between the plates. So now let's recall the expression for a capacitor. Okay, or capacitance means the capacity of a capacitor to store charge, because all the capacitors may or not have the same capacity to store charge. Some may store more charge, whereas some other may store very less charge. Okay, so bringing that into our consideration, and recalling the expression for capacitance, so we know for a capacitor we can write that charge in a capacitor is equals capacitance time voltage, from where we can write C is basically charge divided by voltage. Okay, giving this as equation number 5. Now we are going to use our equation 4 in equation 5. Okay, so I will write using equation 4 in 5. Okay, so 5. So this simple, C equals Q. In place of V I can write Q D by A epsilon naught. So if I cross multiply it, it will be QD into A epsilon naught. So I cancel Q with my Q, and this is the capacitance of a parallel plate capacitor. Okay, one thing you will have to remember in this case, there is nothing, not basically nothing. What we say is that there is air between the plates. Okay, so the medium between two plates is basically air. Okay, so that is why the epsilon naught is taken. If there is any other medium, we know the permittivity will change, so therefore we will not be able to use epsilon naught. So this particularly capacitance of a parallel plate capacitor, which we have derived right now, is when the medium between two plates is filled with air. Okay, so in a later section we will cover what will happen if we put another medium. Basically we are going to put dielectric between the plates, and then we are going to analyze how the capacitance of the parallel plate capacitor is going to change. Okay, but for now our medium between two plates is here, so therefore C is basically A epsilon naught by D. Capacitance means what is the capacity of this parallel plate capacitor to store charge. And looking at this expression, final expression, we can conclude that the capacitance depends upon number one is area of a plate. So area of a plate. So if you are going to increase the area of a plate, so then the capacitance is also going to increase, because you see the linear relationship between A and capacitance. Okay, the second thing it depends upon is separation between the plates. Separation between plates. And you can see out here, if I am going to increase the capacity, increase the separation, the capacitance is going to decrease, because you see there is inverse relationship between the separation and the capacitance. Okay, so if you take two plates away from each other, the capacitance is going to decrease. Okay, because why? Because the separation is being increased. Okay, uh, and vice versa. But if you increase the plate, the capacitance will increase, and that is intuitive also. Intuitively also, we can say the same thing. Why? Because if you increase the area, then I think we think in that way that more number of charge now can be brought into that capacitor. Okay, and third is the medium, because if the medium is going to change, medium between the plates. So if the medium between the plates is going to change, then we cannot write epsilon naught, which is absolute permittivity of free space, which has a particular, which is a constant, which we have value as 8.85 into 10 to the power minus 12. So that is going to change. If that is going to change, that is going to affect the capacitance of a parallel plate capacitor. Okay, so these are the three things that we have to focus on, and after that we can show the variation of capacitance with area as well as the separation. Okay, so next is a variation of capacitance with A and D, so area and separation. Okay, so first let me, okay, so this is my capacitance, this is my area, and similarly next uh, we will show the variation of our this one, this separation and capacitance. You know, the area and capacitance are directly proportional, so you get a linear graph like this, whereas the separation between the capacitance and separation are inversely proportional, so we are going to get a graph like this, which shows the inverse relationship. Okay, so in the next class we are going to introduce a dielectric between the plates, and then we are going to analyze how the things are going to change for a parallel plate capacitor. I hope you understood uh, the lesson, and if you have any doubt, you can put that into the comment section. Thank you.